Hi, I have your notes here for section 9.1, and we're going to talk about ellipses today. So we've already spent some time on parabolas. Now we're going to spend some time on ellipses, and then in the next video that you watch, we'll spend some time on hyperbolas. What are all these things? Let me show you what they are. They're called conic sections. And conic, cone. So a conic section comes from taking a cone and imagine slicing it. So if you took a knife and sliced off the top of the cone parallel to the base of the cone, straight across the top, and then that little piece that you cut off, open it, what shape would you be looking at? You would be looking at a circle. It's called a cross section. You learned cross sections in geometry. When you slice something open and then pull it apart and look at the inside shape that it makes, that's a cross section. So depending on how we slice a cone, that determines what shape of a cross section we get. And it's called a conic section because it comes from a cone. So if we slice it straight across, that's a circle. If we sliced it through the slanted side, if we slice it through the slanted side, we would get a parabola. That's if we, hang on. If we sliced it through a slanted side and came out through the bottom, we would get a parabola. However, tilt our knife up a little bit, slice slanted through one side and out the other. Now our cross section would be an ellipse. It looks like an oval. And these are cool. The hyperbola looks just like a parabola, doesn't it? Okay, hyperbola says, what if, you got to use your imagination on this, what if there were two cones? What if the other cone was balanced, like tip to tip on top of this cone? And if I slice through both of them, I would get one parabola going this way and the other parabola going this way, so it would make two parabolas opening in opposite directions. That's a hyperbola. So, conic sections. We're going to kind of investigate each shape and what the graph of each shape looks like and how we can manipulate it and find out more information about each one. So, back to 9.3. We're looking at ellipses. I want to point out what the equation of an ellipse looks like. So, when we look at an ellipse on a graph, remember they kind of look like ovals. So, our oval, the ovals that we look at will either be long ways horizontally or they will be long ways vertically. We're not going to do any ellipses that are like positioned on a graph diagonally. They'll either be horizontal or vertical. So this is what the equation looks like when our ellipse is positioned horizontally. Now check this out. See it? There's a plus sign there. It equals 1. See it? This is what the equation looks like if our ellipse is positioned vertically. So there's a plus sign. It equals 1. You're going to be given both of these equations. You don't have to memorize them. However, it's going to be up to you to be able to look at one of these equations and real quickly say, oh, I know what it looks like. I know it if it's positioned this way or if it's positioned this way. You have to be able to look at that and tell. And the way that you're going to be able to tell is you're going to check out the denominator. One of these two numbers will be bigger than the other one. One of these two numbers will be bigger than the other one. If the bigger one is under the x that's being squared, then it's positioned this way. If the bigger of the two is under the y, then it's going to be positioned this way. Okay, so you're going to look at an equation of an ellipse, and the first thing you're going to see, once you tell it's an ellipse, so once you identify that you have pluses here and that they equal 1, oh, it's an ellipse, and then you're going to look at the denominators and say, oh, it's positioned this way because I'm looking for the bigger of the two denominators. You need to lock that in your brain because the next shape that I'm going to show you in the next video is a hyperbola. Now I want you to look closely. This is your homework sheet for chapter 9. On your homework sheet is your formula sheet of all the stuff you don't have to memorize. We already did a parabola. We spent 2 days on it. That was section 9.3. Section 9.1 is ellipse. Section 9.2 is hyperbola, right? Look how similar the equations look like. Look how similar they are for an ellipse and a hyperbola. They are so similar. Here's the biggest difference. In an ellipse, these are pluses. In a hyperbola, these are minuses. In an ellipse, you're going to look for the bigger denominator. That tells you how it's positioned. Look for the bigger denominator. In a hyperbola, you're not going to look for the bigger denominator. You're going to look for the positive denominator. And you might say, well, they both look positive to me. Well, kind of. This entire fraction is positive. This one has a negative out in front. So I'm looking for the positive denominator to see which way it's oriented. Over here, you might say, well, they both look positive to me. Nope, they shouldn't. This fraction is positive. This fraction is negative. So this would be the negative one, and this would be the positive one, okay? So, but for now, we're just doing ellipses. You look for the bigger denominator. Let me go back to the notes. Let's focus more on ellipses. Okay, so let's think for a minute. What if this is bigger than this? So this has the bigger number, which means our ellipse is oriented this way. And I need to introduce some vocabulary to you. First of all, the center is the point in the middle of the ellipse. Not all ellipses will be centered at the origin. Sometimes they might be, off the origin a bit. If the ellipse is positioned this way, long ways horizontally, then this is called the major axis. Major axis. The shorter of the two is called the minor axis. Okay? At the end of each major axis, this is called a vertex and this is called a vertex. So it has two different vertices, one on one side, one on the other. And the actual definition of an ellipse is, ready? Oh, hold on. There are two more points that I want to introduce to you. You're going to have 2 points. Each is called a focus, and they're always going to be on the major axis. 2 points on the major axis, and I want you to think of these 2 points as 2 points that are like holding each vertex out so that it creates its oval shape, right? Think about this. Each focus is holding the vertex out so that this doesn't turn into a circle. It's pushing the vertex out. Each focus does that. Vertex, vertex, plural, vertices. Focus, focus, plural, foci. Definition of an ellipse. An ellipse is the set of points. All the points. Equidistant. Just kidding. The set of all points whose sum of distances to each focus is always a constant. So imagine me placing a point here, okay? You ready? Look at this length. See it? Look at this length. Isn't this one longer? Okay, but here's the thing. Add the lengths together. Can you imagine adding those lengths together? You get a number. Anywhere I move this point and I say, go back to this focus, get the distance, go back to this focus, add the distances together. It's going to be the exact same. These two added together, or if I made my point over here, these two added together, or if I made my point here, these two added together, I'll always get the same sum. That's what an ellipse is. Anyway. Focus. Oh, okay. I gotta tell you where the A and the B come from, and the C. So on your major axis, the distance from the center to a vertex is little a. The distance from the center to the edge of the minor axis is little b. Now think about this. Major axis. If A is linked with the major axis, isn't this red length going to be bigger than this blue length? Because the major one is the longer of the two. So this distance is going to be bigger. Go back to your equation. Remember how I said you're going to be able to look at this and say, oh, I see which number's bigger. I see which way my ellipse is. So in the picture that I just showed you, A was bigger. A would be here under the x squared. These are linked together. It's longer on the x direction. If the parabola is positioned long ways vertically, then the longer of the two segments will be underneath the y to let you know. So this will be bigger. This will be bigger than this. These are linked together. It's going to let you know that it's positioned this way. Okay. So I've told you what A is. I've told you what B is. There's one more distance that we need to talk about. So this is A, thus, this is A, right? This is B, therefore this is B. And one more distance that I need to throw at you is to a focus. So from the center to a focus is called little c. All right, now let's go underneath here and let's fill out some information. According to this picture, how long is the major axis? The major axis goes from this red point to this red point. If this length is A, that length is A, thus the whole length of the major axis is 2A. Minor axis. This blue piece is B, this blue piece is B, minor axis 2B. From the center to just one focus is called little c. From a vertex, that's like a major vertex, to the center is little a. And co-vertex, that's like minor axis to center is b. Now, I'm going to come over here to all this information. What I've highlighted in pink is given to you on your formula sheet. Also, these lengths right here have a really cool relationship within an ellipse. Within an ellipse, vertex to center, a squared minus this goes with major, this goes with minor. This squared minus this squared equals this squared. So the ABC relationship in an ellipse is this, given to you. You don't have to memorize it, just be able to use it. Everything else here, I do not use. Remember how I crossed those out with a parabola? This is all different. It's all different when it comes to an ellipse. I cannot memorize all that and keep it straight. You know how I'm going to keep it straight in my head? I'm going to draw a sketch every time I need to do a problem. Just a quick one. It's not going to take long at all. All right, and then I will mention E eccentricity. It measures how ovally the ellipse is, and the ovalness is eccentricity. It can be found by taking C over A. So you would take this distance over this distance. And the closer this fraction, this value is to 0, it's going to look more like a circle. The closer this is to 1, the more ovally it's going to be. Don't worry, you don't have to memorize that. You don't have to memorize the eccentricity formula. That's given to you also. Let's start doing some problems together. So, example 1, we're going to write an equation of an ellipse. And it's going to look like one of these two pink equations up here. Here we go. Right now, I don't even know how it's oriented. We're going to find out. We're going to put our center at the origin, so I've already put a dot there at the origin. See it? The major axis has length 10. At this point, I don't know whether to go 5 and 5 or whether to go 5 and 5. I don't know by that, but it tells me the foci are at positive 3, 0 and negative 3, 0. Hang on. I'm going to color those orange. I'll try to keep it the same. So 1, 2, 3. 1, 2, 3. I'll put a little F there for foci. Now, remember what I told you about the foci? The foci are always on the major axis because they kind of like hold out the end points to make it a little more stretchy. They won't make it look like a circle. So that tells me that my major axis is right along here. So for my major axis, I'm going to count out to 5, either direction. And my ellipse looks kind of like this. I don't know, something like that. But here's the thing. I don't know where these are. I don't know where to make my tick marks for these other endpoints. So when I go to make the equation, ready? I'm going to use this one because it's positioned horizontally. I'm going to put my center here and here. Let's go ahead and do that. Let's put zeros in. Yes? What's A? What goes underneath here? Well, look for your major axis. Your major axis is this way. That what we know what this is going to be the bigger of the two numbers. And A is 1, 2, 3, 4, 5. A is 5. I don't know what B is. I don't know what this is. How do we find it? Well, I know what A is. I know what C is. We can figure out what B is. It goes C squared equals A squared minus B squared. Okay, and I'll let you solve it, but I get that B is 4. When I square everything and try to get B on one side and everything else on the other, I get that B is 4. So I'm going to go ahead and simplify this. You okay with that? I'm just going to call this x squared. I'm going to call this y squared. That's a 5. That's going to be a 4. So final answer, x squared, y squared, and 25 and 16. There you go. That's the equation for that ellipse. Bigger number under the direction that it's positioned. Moving on. Find the equation. First thing I'm going to do is identify the center. The center is at 2, -1. Now, there we go. It's positioned vertically, okay? So A is going to be the longer of the two. So that's A, which means this is B. Okay, let's start our equation. The center is at 2, -1, so that needs to be a 2. That needs to be a -1. Just kidding. Just kidding. You all caught this probably 3 minutes ago. My bad. I wish you could have told me. Center's at 2, +1. Anyway, and then this A is 2. Put it under the Y. And put the B under the X. Right? And to simplify it, just call that 1 and call that 4, and you can be done with it. Done. Okay. Now, for these, they're in polynomial form, and we're going to have to get them to standard form. We need to, turn them into fractions and figure out what, all that stuff. So the first thing that I need to point out to you is this number should be a 1. So what I want to do to turn this into a 1, I want to divide all 3 terms by 36. Watch what happens when I do that. Divide by 36. divide by 36, divide by 36. I get, 4 over 36. I think that reduces. Hmm, 9 over 36. I think that reduces. Sure enough. Now, it says tell whether it's a circle or an ellipse. Here's what's cool. If these two numbers down here, if the bigger one tells me which direction it's stretchy, what if they were equal? What if neither one of them was the bigger one? So it wouldn't be stretchy in either direction, and it would be a circle. Is this an ellipse or a circle? Well, this would be 3 squared, this would be 2 squared. These numbers are obviously different, so it's more stretchy in the x direction. So it's an ellipse. Okay. No parentheses here, so my center is at 0, 0. A is 3. B is 2. I'm going to go down here and, oh, I wish that wasn't so far down. Okay, I'm going to go down here and plot everything that I know. Center. It's stretchy on the x, so 1, 2, 3. 1, 2, 3. B is 2. Right, that's what my ellipse looks like. Now, it's asking for the points. Give me the ordered pairs. Y'all can do that. So, the vertex, gonna be at positive negative 3, 0. Yes, with me? That's the major one. The co-vertices are going to be at 0, positive negative 2. I've already said what the center is. Check, got that. Oh, it asks for one more thing. Give me the points for the foci. Well, we know they have to be along here somewhere, right? Along the major axis to hold this out. The foci have to be along here. Let's figure out where they are. So I'm going to go c squared equals a squared minus b squared. With me? C is a yucky number. C is radical 5. It's like radical 5. I don't know. 2 point something-ish. I don't care. 2 point something. So the foci are like here-ish. 2 point something. Negative 2 point something. Give me those points as ordered pairs. Well, this direction would be positive radical 5, 0, negative radical 5, 0. And I think I've answered everything. At the center, the vertices, the co-vertices, the foci, I've sketched the graph, all good. Oh, eccentricity. Did it say eccentricity? Yep. One more thing. E equals C over A. There we go. There's the eccentricity. Moving on. This video's getting long, and we've got to do another completing the square problem. So I'm going to go as fast as I can. You might need to pause and slow down. And we need to get this equation separated and looking like a standard form, one of those pink equations that we had highlighted. So here's the first thing. I'm going to take you step by step. Ready? Group your x's together, group your y's together, everything else on the other side. I grouped my x's. I grouped my y's. I moved the 211 over to the other side. Okay, now, two things. I want you to pull the coefficient off the x and pull the coefficient off the y. So just from these two, I want you to factor out a 25 and then put a plus sign. And then off of these two, I want you to factor off a 9, okay? Watch me, watch how I set it up, and then pause it and go. Here I go. 25 parentheses x squared minus 8x, leave a space, pull off the 9. Y squared plus 4y, leave a space, equals negative 211. Pause it, do that. Now, here's what I'm ready to do. This, I know there's 25 out there. This needs, the parentheses need to turn into this, which needs to turn into this. And we did this in the last video. We need to complete the square. So I want to know what this number needs to be so that this factors into two identical binomials so that I can write these as one binomial. All right, so since this is negative 8, I think this should be x minus 4 and x minus 4. What should that number be? Good, plus 16. Here I go. Plus 16. Hold on. Did I just add 16 to the left side of my equation? Nope. I just added 400 to the left side of my equation. Y'all are going, what? 400? Wait, where did 400 come from? What is each of these things in my parentheses being multiplied by? 25. Because the 25 is out there. Big picture, I just added 400 over there. 25 times 16 is 400. I just added 400 to the left side of my equation. Go to the right side, keep it legal, add 400. Plus 400. Let's figure out this number. While we're still on this topic, let's figure out this number. So, again, that's our goal. These parentheses need to be factored into two identical parentheses so that we can write them like this. So, I think this should be y plus 2 and y plus 2. Don't you think so? Y plus 2, y plus 2. What do you want this number to be? I want it to be a plus 4. Right? Y plus 2, y plus 2, I want that to be 4. Did we just add 4 to the left side of our equation? Nope. We really just added 36 to the left side of our equation because you got to figure out that, or you got to factor in that that 9 was out there. Supposing to be multiplied by every item in there. So we just added 36, keep it legal, add 36. Okay, so the 25 is still there. This factors into x minus 4, x minus 4, y plus 2, y plus 2. Okay, now I'm going to change this to look like this, but the 25 is still there. So I got 25 and the 9 is still there, and this is y plus 2. And on the right, negative 211 plus 400 plus 36 is 225. Okay? This needs to be a 1. This reduces. This reduces. This is an ellipse. Center is at positive 4, comma, negative 2. This is bigger. Major axis this way. A is 5, B is 3. I'm going to plot the center here real quick. 4, negative 2. 1, 2, 3, 4, negative 2. There's my center. A is 5. 1, 2, 3, 4, 5. 1, 2, 3. Oh, I ran off. No big deal. B is 3. 1, 2, 3. 1, 2, 3. That's what my ellipse looks like. When you're asked, give me the vertices. Okay, well, name that point and name that point. You got this. Give me the co-vertices. Okay, name that point, name that point. You got this. Give me the foci. You got to do some math first. C squared equals A squared minus B squared. Oh, that's easy. 4, major axis. Remember, it holds them out. So from here, I'm going to count out 4. 1, 2, 3, 4. Foci, where are they? Name those points. That's all you got to do. I'm not going to finish it out because I've gone long enough, and I think that you all are smart enough to name points on coordinate planes. So I just wanted to make sure you could do the completing the square again. That was a tough one. All right? Good luck.